Well, hello everyone, and welcome to the Pavilion webinar, Shatter Your IO Bottlenecks and Get More from Your Data Than You Ever Thought Possible. My name is Keith Parker. I am the Director of Product Marketing here at Pavilion, and I'm joined today by Costa Hasapopoulos, our Chief Field Technology Officer. And with that, let's go ahead and begin the presentation. So when it comes to shattering bottlenecks, Costa, could you move the next slide, please? When it comes to shattering bottlenecks, the thing that's really driving the need to do that is customer applications. It's what the organization is trying to achieve. And as we've moved into a modern data-centric world where data-driven applications are enabling organizations to extract more value from their data, it's these applications that are really driving the need for greater bandwidth, greater throughput, greater speed. It's applications like artificial intelligence, machine learning, deep learning. These are the things that organizations are either doing today or are looking at doing in the immediate future. Almost every major organization out there is either actively working with some type of AI initiative or planning to do so in the very near term. And that's really going to have a fundamental impact on what they can do as an organization. When you look at media and entertainment organizations, they have huge bandwidth requirements. It used to be just, video editors were the only ones who needed it, but now it's capture, it's ingest, it's getting that information. It's where you have something called volumetric data capture, where you might have literally hundreds of cameras capturing information about a particular scene to go ahead and create a virtual world that the actors will then operate in. It's ingesting that data, it's making edits to that data. One of the things that they're doing is, in the case of a movie, you might have a movie distributed in dozens of countries and dozens of different languages. Well, someone would actually go through, and if there's, say, someone holding a magazine or a newspaper, someone would actually keep an eye on that entire thing and follow it through and pull out every individual frame where that magazine is shown and change each individual frame to show the local language for every place that movie is going to be distributed. And that used to be a process that would take weeks that now takes hours because they're applying AI algorithms to go ahead and do that. Virtual environments, pretty much every data center on the planet has some form of a virtual environment, whether it's running multiple VMs or containers or, everyone's going to have something in that. And what that needs is it needs better throughput to go ahead and enable the existing infrastructure to support more virtual machines, more containers, ultimately reducing cost. Image recognition. Image recognition has become a huge thing in terms of providing security, providing analysis, even just basic individual systems to let people in. Analytics. Large-scale data analytics has become so important to every organization. The ability to bring in data, perform some type of analysis on it, whether it's market data or customer data or product data, being able to analyze huge volumes of data, not just recently, but over time, is really driving the need for throughput, as well as in research, where the need to fundamentally push the bounds of science and develop new treatments is more important than ever. And when you look in, and Costa, if we go to the next slide, when you look at the needs of these applications, what you're seeing is you need to do things faster, do things better. With AI and ML, the need to train artificial intelligence models has never been more critical. And that's really a function of how much data can you bring in, how quickly can you do it. The more data you can bring in faster to keep GPU-based systems, which really these applications are running on, keeping those GPUs saturated so they can process that data and train those AI models as fast as possible is vital to organizations. Bringing data in for image capture, for processing, reducing time to production, getting those media assets out to the public as quickly as possible is so critical to costs. Virtual environments. When you can cut the number of systems that are required to support your virtual infrastructure, when you can take your existing infrastructure and twice as many VMs, run more containers, what you're effectively doing is you're cutting costs in half, because it's not just the hardware that you don't need to buy more of, it's the need to not license software to run on those cores, on those systems. You can cut your costs in half by improving performance. Facial recognition, you can cut times to threat identification, to solving problems, to letting law enforcement solve problems before they happen. Analytics, getting data faster is so important. If you can, use say a GPU-based system to run analytics in real time for a quarter's worth of data. What if you could run that same information, that same analysis on 10 years worth of data, because you have larger data, faster data that can provide the information as needed? And for life sciences, I mean, we've all lived through this past year where the ability to process data, analyze information, generate results is really going to save lives, save so much that we need in the world today. And the thing that's really driven all this, the need for a new type of storage, Costa, if you want to move to the next slide, has really been the tracking, as we've seen the evolution of technology over the last decade. We've seen processors dramatically rise in performance. Not just CPUs, but the advent of GPUs have enabled these applications to do so much more, so much faster. Memory's gotten faster, 100 times faster over the past decade. So we've seen huge jumps in processing, in memory, and even network speeds. We've gone from 10 gigabit Ethernet to now 400 gigabit Ethernet is actually shipping. We've seen networking overwhelmingly become much faster, but storage hasn't actually kept up with that. And the primary reason storage hasn't kept up with that, there have been advances. There have been things where we've moved from, spinning disk to flash. We've moved from, SCSI interfaces to NVMe. We've seen big changes in some of the interconnects, but the fundamental problem really lies in the architecture. If you were to look at a storage array from 10 years ago, or even 20 years ago, the basic architecture would not be fundamentally different than the latest all-flash array you might get from just about any vendor today. It would still be a basic dual controller system. Now, sure, some of the interfaces and things might have changed. 15 years ago, you might have had an Ultra 160 SCSI hard drives connected over 1 gigabit fiber channel, and today you've got NVMe flash drives connected over either Ethernet or fiber channel with those different vendors. But the fundamental architecture, that dual controller architecture, is still going to be there. And that's the thing that's been holding storage back, is that dual controller architecture. And Costa will go into some detail about how we've reimagined storage and created a new type of solution that can fundamentally deliver greater performance across the board for every application. Costa, if you can go to the next slide. And this has been this is not a new thing. This is something I like to talk about. This was Ken Batcher. He was a professor at Kent State University, and almost 50 years ago, he made the comment that a supercomputer is a device for turning compute-bound problems into IO-bound problems. And that's exactly what we've seen. As processing has gotten faster, as networking has gotten faster, storage has really become that bottleneck we need to shatter to really unlock what our applications can do. Next slide, please. And following on to that, this is a quote from just a few months ago from Roger Cox, an analyst with Gartner, who's fairly well known in the industry. And his comment was that next generation data-centric workloads like artificial intelligence, modeling, and simulation require bandwidth, latency, and IOPS performance beyond the capabilities of NVMe technology-enabled dual controller scale-up all-flash storage arrays at scale. And he's essentially saying the same thing I'm saying, which is to deliver on the performance needs that next generation applications require, we need something beyond that dual controller architecture that's been prevalent in storage for decades now. Next slide, please. And that's what we're going to talk about today. We're going to go ahead and talk about how we can, the Pavilion hyperparallel data platform can deliver the most performance, the most density, the most scale, and the most flexibility of any data storage platform in the universe. And we're going to go ahead and talk about that in terms of performance. We'll talk about that in terms of throughput in gigabytes per second. We're going to talk about that in terms of latency. We're going to talk about that in terms of IOPS. And we're going to deliver that in an incredibly dense 4U platform, a platform that you can scale. You can scale up within the platform. You can start with as few as 4 controllers and scale up to 20 controllers in that single platform. You can start with as few as 18 drives and scale up to 72. It is flexible. It will support block, file, object workloads with best-in-class performance for each one using a variety of different data storage protocols. It is the most performant, dense, scalable, and flexible data storage platform in the universe. And with that, I'd like to go ahead and hand it over to my colleague Costa, who will explain exactly how we were able to deliver such incredible performance in such a dense, flexible platform. Costa?
Great, thanks, Keith, and welcome everyone to the webinar. I'm going to focus on how do we do the things that Keith said, and really how do we enable that unrivaled data storage choice and control. So I think I'm going to talk about 3 major areas here. One is about flexibility and performance. I'm also going to talk about a new version of our HyperOS software. It's the software that runs on our current hardware that's coming out in a few weeks. And we'll talk about our NVIDIA partnership. We are an NVIDIA storage partner, and some testing that we have done on the NVIDIA platform. Let's start with that flexible performance, and I'll end up in some solutions and use cases. So let's start with, Keith alluded to that our architecture is fundamentally different. I think some things is where we came from is what makes us different. First of all, when our founders started with our platform, we started looking more like a network switch than we did a typical storage array, because the founders were storage and server and networking guys that brought in the storage expertise. So we're built more like a network switch. We were built from the ground up to support NVMe drives and NVMe over Fabric. We were built from the ground up, not for dual controllers. We'll call it not multi-controllers, many controllers. So the first differentiator for us is that yellow area here. This is our PCIe switch. So that's an any connectivity to any one of our devices in there. So built on a network that's measured at nanosecond speeds, right? We have 20 independent controllers, right? Not dual controllers, right? 20 of them independently operating with each other, right? And then with each one of those has their own CPU, memory, and network. When you look at this drawing, the drawing on the right is a top view. The drawing on the left is the rear view. We can support up to 72 U.2 NVMe drives. And we can start with 18 and add another bank of 18, add another bank of 18, and add a 4th bank of 18. All of this packed into these storage controllers, where I said those 20 independent controllers that I point to on the right. On the left in that rear view, each one of those vertical cards is called our line card. And a line card consists of 2 controllers, not dual controllers, 2 controllers. They have their own network ports, their own memory, their own CPU, and their own PCIe connections through that switch to every one of the NVMe drives. We can either have up to 40 100 gig Ethernet or InfiniBand ports, or 10 200 gig EDR, HDR InfiniBand ports, giving you that flexibility. But what's really impressive is that what you'll see later is those 18 drives could be up to 2 petabytes of usable capacity, 20 controllers, and up to 40 100 gig Ethernet ports in 4 rack units. Just so everyone remembers, 4 rack units is 6.9 inches. So incredibly dense. Any one of our controllers had any drive connectivity. We do not have a concept of cache. We don't have a concept of tier. We have several software patents that allow us to do impressive direct memory access from our controllers to multiples of our drives, not for data, but also for metadata. We have RDMA connectivity, all from our hosts to the Pavilion box, all using standard protocols. And as Satish, one of our founders, says, our hardware, our software is designed to take unfair advantage of our hardware. So in continuation of why we're different, I'll give you some of those. I gave you the big picture, give you some of these specs. That switch, 6.4 terabit switch, 72 NVMe drives, 40 100 gig Ethernet or 10 200 gig Ethernet ports, 4 rack units, right? We see in testing after testing, we get similar performance or even better of somebody having NVMe drives in the physical server that they're running, and then logically taking those same drives and put them over a network in a Pavilion box and get similar or same performance over the network because of our technology. And you'll hear a theme of us is flexibility. You'll hear another theme of consistent, predictable, scalable, high performance at ultra low latency. That seems like a long word, but it is because all those things are important in the workloads that Keith discussed. You want to assume that every server gets the most bandwidth every time in a consistent, predictable manner. So these results of this flexible storage platform, we believe are pretty impressive in really 3 dimensions. Keith mentioned one of the dimensions, density. So in those 4 rack units, we can have up to 2 petabytes usable, about 2.2 raw. It'll deliver 20 million IOPS at a very good power profile, 3,200 watts. We've actually never seen it take 3,200 watts. That's the max. 20 controllers, 40 gig. You then take that column on the right. If you were to normalize this against the competition, everybody has different rack units and all this. We'll just take that and divide everybody by the number of rack units that they have, and that's the measure of what can you deliver per rack unit. Per rack unit, we deliver half a petabyte of capacity, 5 million IOPS, and 10 100 gig Ethernet ports per rack unit. So not just density, but flexibility in the storage type. Any one of these controllers, and I'll show this later, could either be configured to run block, file, or object, or any combination of the controllers. Multiple protocols, some of them block protocols, some of them object protocols, some of them file pro. So the flexibility in the type of storage, but then not only the type, it's the protocol that you access that storage type. All of this, and you'll hear me use the words best in every class, not best in class, in every class. Because when somebody says, compare us to the competition, well, you're comparing our block, you're comparing our file, or you're comparing our object. So I'll put the challenge out to any of our competitors. I'll get in a running race, or we will get in a running race with any of our competitors in any one of these storage types. Here's our block, file, or object. In our block, 120 gigabytes a second read, 20 million IOPS at 100 microsecond latency. In the area of write performance, which is very difficult to do in most platforms, but our write performance is typically about 75% our read, which is incredibly impressive. We deliver 90 gigabytes a second write at 5 million IOPS at 25 microsecond latency. So everything is really low latency, super high IOPS, whether that's large block or small block. Then you turn it into the file protocols, up to 90 gigabytes a second read, 56 write. Object, 80 gigabytes read, 35 gigabytes a second write. So we believe that's best in every class in each one of those. So not just performance density, but flexible performance density. And then we also need to say this right up front. You're not paying a premium for this ultra performance. This is all at market competitive prices, what you'd expect to pay for an all NVMe system. So people ask us, well, 20 million IOPS, 120 gigabytes a second, 90 giga, what am I going to do with all that? Well, the first thing is you might not start with that. You don't have to start with 20 million IOPS. You can start with our smallest configuration, 1 group of drives, 2 of what we call our line cards, which is 4 controllers. Remember, there's 2 controllers for each one of those cards. Those 2 in the middle are supervisor cards. They're just for our control plane. You could start with a couple of those controllers running a block protocol with that capacity of 18 drives. Remember, those could be up to 30 terabyte drives per drive or as small as 3.2 terabytes. So the capacity depends, right? But you could start with a capacity with a couple block, and you may decide that, you know what, I have enough capacity, but I now want to add some more horsepower and run file protocols on a couple controllers. You can do that. So you can scale performance independently of capacity physically inside the chassis. You can then add some more capacity because you have enough performance. Add more performance, but you have enough. You see the drill is you can scale these things independently inside the box. And so, again, you may not start with 20 million IOPS. You may only start with 4 million IOPS. When I say only start with 4 million block IOPS, 4 million block IOPS is almost better than everybody else on the planet. And that's our smallest configuration. All this is linear scalability. Every time you add a storage controller, because it is an independent instance of its hardware and its software, it's linear performance. Effectively in block for every controller, it's 2 million IOPS, right? Or excuse me, 1 million for every single controller. You have 2 controllers, it's 2 million. You have 4 controllers, it's 4 million. You have 20, it's 20 million IOPS, okay? All at ultra low latency. We also give you that flexibility in how you want to deploy it or use this system. You could use it and be all block. In other words, all your hosts are just running some block protocol, NVMe, over Fabric, iSCSI, whatever the block protocol is you choose. You could be using us to leverage a large external file system like IBM Spectrum Scale or Lustre or BGFS. And in that context, we're actually block storage to Spectrum Scale, Lustre, and BGFS, and they present NFS or whatever protocols up to the clients. So flexibility of deployment in block. But you may choose to run us as an object protocol and leverage our software to turn that hardware into an S3, very high performant S3 interface. Or run that in a high performance parallel file system where you have multiple of our boxes connected together. So again, whether you're deploying as block, file, or object, whether you're using our file system or somebody else's files, again, flexible performance density, right? And so when we look at what's coming in our 3.0 release, which is being released here in the next couple weeks, right? There's some enhancements to block, some enhancements to file, and enhancements to object. From a block perspective, we're doing some really unique things to take our current OS that runs our platform called the HyperOS, right? And this new version will support containers. The first applications that are supported inside those containers are our new parallel file system and our new parallel object storage system. We have some enhancements to do QoS support. We now have a Windows NVMe TCP driver. It's very important for large media and entertainment environments, as well as big SQL Server environments, as an example. Support for 2 petabytes raw, and we have lots of enhancements to high availability features, right? We're going to drill into one of those key features in the block side, then we'll get into our parallel file system, is we've really introduced 2 unique things: controller failover flexibility and some unique things in what we call data assurance. So because we have many controllers, you could have, let's pick 5 controllers, 1 through 5, and each one of them have their own active workload. That's the A in the green. And they could act as standby for another controller. So 1 could fail to 2, 2 to 3, 3 to 4, 4 to 5, and 5 back to 1, as an example. And in that use case, all those controllers can have an active workload, and another one can fail over. Just like every other storage appliance out there, you have to, as you apply workload to controllers, if you put too much workload on a controller, when it fails over, you could have less performance in the failover degraded state, because if you put more than 50% workload in any controller, when it fails over to another one that has 55, then there could be performance challenges. It has nothing to do with Pavilion or anybody else. It's how you use the workload. We have the ability, because we have many controllers, we could use those same 5 controllers, but only put active workload on 4 of them, and all first 4 fail over to the 5th. Now you may say, well, I'm wasting money on a controller that's not going to be used. Well, the fact of the matter is the controllers aren't that expensive. The second piece is it now allows you to not worry about how much workload you put on controllers 6 through 9, because let's say every single one of them had 80% workload on it. When 6 fails, it's going to a controller 10 that has no workload. It has the exact same performance as it had in before its degraded state. There is no degraded state. We call that kind of a spare controller or controller RAID. We believe we're the only platform on the planet that can do that because of our multi-controller architecture. The second piece is, of course, we support T10 diff, which protects from drives that have bit rot and all the things that are just fundamental issues with SSDs. We took that one step further. what we call metadata versioning. This is patent is pending, is one of our 30 patents on this technology. And as drives get bigger and bigger and their workload gets bigger and bigger, drives have a potential to drop a write and do some other challenges in their destaging of the drive cache to the, has nothing to do with Pavilion, has nothing to do with EMC or Dell or anybody else. It's just the way the drives operate. We built a technology that when we do a write, we not only put the RAID and the T10 diff information, all this into each 8K block we write on the drive, we put a version number in there. We store that same version number in our own metadata. So when we do a read, we make sure that what we said was written was also really written on the drives on read. If not, we'll rebuild it from parity. That's a patent pending only from Pavilion. I said we support now a Windows NVMe driver for TCP, impressive single client performance in the Windows space. You'll see a Rocky version or the RDMA version coming soon. And again, why is that important? Very large SQL Server environments is a great use case of that. More queries, more workload, more ingest, impressive workload and post-performance video transcoding. Keith alluded to that in the early on. A very large percentage of that Hollywood entertainment work is done on Windows machines. We can deliver incredibly high throughput direct to each Windows machine. Let's change gears now and look at what we're doing in our new HyperOS 3.0 from a file perspective with our new hyperparallel file system and our new parallel S3 object storage system. So again, back in those ways, whether we block, file, I'm going to now focus on our file and our object solutions out there that's going to be released here in the next couple of weeks, right? Again, on our platform that's in production today, we do have a version of file, we do have an object that's been in production for almost a year now. We're introducing a new version that adds material new flexibility, and we'll talk about that. As I mentioned, this is a foundational upgrade. Our current operating system is called 2.5, 2.x, right? And all that red area is our storage services, and it goes up vertically as our control plane running protocols. And as I said, the first thing we did was introduce container support. The first two applications that run on those containers are our new global namespace or hyperparallel file system and our new global namespace for object or our parallel data S3 object storage, right? These new object storage now cross physical chassis from Pavilion. In our 2.x, they stayed on the single chassis, and I'll talk about that. I talked about the block. Now we're going to talk about the file and object. From a high-level perspective, I'm going to go into a little more detail. Multi-controller, multi-chassis, distributed file system. In other words, outside the chassis, acting as a single namespace or single mount point. You will see single node performance or aggregate performance, either one, 75 gigabytes a second read plus 50 gigabytes a second write plus. And the reason the plus is there is we're not released yet. We're finishing our testing, but that's the testing that we're getting today. You'll see this in a single or multiple namespaces, multiple connectivity types. I show more details later. Tiering, security, replication, encryption, snapshots, and clones. Same thing in an object, multi-controller. Very impressive multi-node performance, multi-chassis, 60 plus for read, 40 plus for write. This is native cloud object storage, S3 interface. You actually have a way that you can access it via a normal file system interface as well. Things like worm, tiering, replication, security, all the things that you would expect in an object storage. But don't think slow object, think high performance object for next generation applications. So we look at that flexibility word. So if you had one of our chassis out there, you could choose to bring your own file system, Spectrum Scale, GPFS, block, and running ext4 or one of these other block file systems for a single host. You could use our file system, our global namespace. You could use our block, you could use our object. If you're using our block, here's the protocols you can use. If you're using our object, you can use the S3 protocols. There's some plugins that we have for native applications, which I'll show you later. If you're using our file or NFS protocols, you have a myriad of ways that you could access our box. Gives you that ultimate deployment of flexibility, and I'll show you that. Whether that's to one box or a cluster of multiple of our boxes, all acting as one single mount point. So when we talk about this high performance file systems, whether that's for NFS or whether it's for S3 or object, right? You could have one of our systems be all NFS and a single mount point. You could have one of our systems be all S3 and a single mount point for S3, or any combination. You have the flexibility to say, not just one chassis, multiple chassis. You could have, there's no theoretical limit to how many chassis we could cluster together. I'm drawing this with a ... At our first release, we'll test up to 8 chassis. Again, there is no theoretical limit. It's just a time and hardware testing. And you'll see later, those 8 chassis is 600 gigabytes a second. It's 32 petabytes of storage, 16 petabytes of storage in 32 rack units. So it could be all NFS, could be all S3, or some combination of the two. But again, when you look at this, we have the ability to take and look at this from a client connectivity perspective. You may have one or many of our boxes in a single cluster for the Pavilion hyperparallel file system, our NFS, right? You could make that a single mount point across multiples of our chassis, again, tested up to 8. And you may choose on the client standard ways to access that single mount point. Every one of these ways I'm going to describe to you comes native in typically every modern version of Linux distribution. There's no software they need to install from us. These are things that are just, you turn on features in Red Hat, in CentOS. They just come native with it. You can choose to have all your clients or hosts out there to be running NFS v3. You could choose to be NFS v4. You could choose to be NFS RDMA, PNFS. There's a Gluster client. There's a Spark client. There's a Hadoop client. Or you can choose to intermix those protocols and clients, all accessing the same mount point. Of course, there's trade-offs of why you would deploy each one of these protocols. There's trade-offs if you want to do multiples at the same time, but we give you that ultimate flexibility and choice. Because at the end of the day, in a hyper-parallel file system, we are the most flexible in the world and give you guys choice and control. We look at that interoperability and flexibility. Oops, excuse me. I hit the wrong slide. So it's not just flexibility, but flexibility to scale in the chassis as well as cross chassis. So inside the chassis, in one of our chassis or one of the Pavilion boxes, if you filled it all up, running our file protocol, you'd get NFS of about 75 plus gigabytes and write bandwidth of 50 plus, right, to a single mount point. But remember, you don't have to start like that. You could start with 1/4 of that and get 18 gigabytes a second read and 12 gigabyte write and 500 terabytes, half a petabyte of capacity. You can then add some more controllers and more capacity and double that performance. A little bit more, triple it. A little bit more, quadruple it to the chassis in 4 rack units, 2 petabytes of capacity, and you see the 75 plus and 50 plus in a single chassis. You also have the flexibility to go cross chassis. So I'm going to pick one that's the full box. And every time you deploy 4 rack units, you get 75 read, 50 write, and 2 petabytes of capacity. You add a second box, you double it. Single mount point expands now to 4 petabytes. Third box, you triple it. Mount point expands to 6 petabytes. And you see the performance linearly scales. 4 boxes, 5, 6, 7. I'm just giving you an example of 8 boxes. Single mount point. That will deliver in 32 rack units. Remember, a rack is about 44 rack units. So, not even a full rack. 32 rack units, 16 petabytes capacity, 600 gigabytes a second read, 400 gigabytes a second write. Massive performance, massive scale linearly. I don't build out the slide, change the numbers to be 50 and 30 for object. What I just described works exactly the same way for object. It's just the per chassis is a little bit smaller. from a performance perspective. Capacity is the same, but performance is a little bit less. Incremental performance, linear performance, scaling inside the box, starting small or growing, or scaling outside the box, starting small and growing big. As you look this, what are the use cases for this fast NFS, this fast block, or even this fast object? Keith alluded to them. I'm going to talk about how do we solve some of these problems, right? And one of the things is we're seeing a lot of work is people doing AI and all sorts of things, and that's this NVIDIA world. And this is an NVIDIA partnership. We've done a lot of testing of how can we perform in this space, right? At the Supercomputer show 2020 happened back in November. That's Michael Kagan, the CTO for NVIDIA. And there was an NVIDIA kickoff or a keynote, and he was one of the speakers inside that keynote. And during his time speaking, he had 2 slides up there. I'm showing one of them that had Pavilion mentioned in there. And some of the things that I wrote down of what he said are not necessarily directly related to Pavilion. They were talking about storage. And I'll put a checkbox of, do we address that problem? High performance computing requires high performance IO. Well, that's what we do. The rule is simple. The higher the processing power of the compute element, the more data it can process, hence faster delivery, data delivery is required. Checkbox Pavilion. In particular, he did say, he was referring to that purple area of that slide, because we were testing using our box with filling GPUs through the CPU where it normally works, as well as a new technology called GPU direct storage that is some code that runs in CUDA code on the DGX A100 is what we did, or any system, that bypasses the CPU. His comment there was performance improvement using GPU direct storage, and we were in the file protocol of almost 4 times not using GPU direct. Another quote, just in general, storage access is yet another bottleneck that needs to be resolved. Again, checkbox Pavilion. So we've definitely caught the attention of NVIDIA. If we layer on those performance numbers I showed you early on, those are kind of hero numbers. What I should have mentioned is every time we measure our performance in that far right column, that is all data that's protected by data protected with RAID 6. So no cheating on RAID 10 or anything like RAID 6. Also measured at the sum of the performance of the hosts, not the ingress and egress of the box. So we consider the network latency to talk to each one of the clients. So we're still getting 25 microseconds block, 100 microseconds read with the network latency in there. So you take that and then layer into doing testing that we did with on our NVIDIA box, our DGX A100 with some testing, and said, what could we do leveraging GPU direct storage, this new technology, as a testament of how hard can we drive a Pavilion box and what could we get out of it. And in our testing, it took 2 of our Pavilion boxes to a single DGX to provide, to keep those GPUs full of data all the time and writing them. We were able to do that using a file protocol, NFS RDMA. We were also able to do that using a block protocol, NVMe over Fabric, Rocky, right? We're in the process of testing that same thing with InfiniBand. We believe the results will be exactly the same. But 2 of our Pavilion boxes delivered 191 gigabytes a second and 1.7 microsecond millisecond, and 118 write and 5. Those are data coming from a Pavilion box through the whole DGX and filling up the GPUs. Just to note that we did this with one of our boxes, and because we scale linearly, and as well as the DGX can be configured to do half a system, and then we opened it up for another half of the system, we extrapolated those numbers to 2 to support 2 of them. So in 8 rack units, we delivered that information. So when you look at some of our advantages out in the GPU world, whether those are NVIDIA GPUs for a DGX or whether those are GPUs in an HP or Dell server, the real value for us, especially to solve this, is the deep density that we have, 4 rack units and 2 petabytes of capacity. Our super high performance and ultra low latency, whether that is read, but also impressive write performance. What I always tell people, when you're talking to our competitors out there, when they give you some of their numbers, don't let them just give you one number. Ask them what their read latency is. Ask them what the write latency is. What is their big block read performance, big block write performance, small block write performance, small block read performance? Ask all those characteristics. That's why we publish every single one of them, but because we know our numbers are incredibly impressive in every one of those classes. So ask the second question to our competition. The other value that we live in this GPU space is for some of this newer technology that's coming out for GPU direct storage or even non-GPU direct storage. We support NFS and block, file and block on the same platform, gives you that flexibility. All of ours is open standards based, no special host add-ins, right? All standard protocols that come with standard Linux distributions. We also did some testing with one of our partners where they have an in-memory GPU based database. Company is called OmniSci, very impressive company. And we did testing that they tested their database and their ecosystem and said, let's say all the data starts on the 4 drives that fit inside the DGX A100, those NVMe drives. And they got performance X. The number doesn't make any difference. It's performance X. Then you effectively take those same drives and put them inside a Pavilion box over an Ethernet network to a Pavilion box. And when they did their testing, they effectively got performance X. It's a testament to our architecture from a hardware perspective as well as a networking performance. So for them use case, they effectively got unlimited capacity because now they can have their storage outside in a shared storage environment, right? So when I said earlier, similar performance to DAS with all the benefits of shared, right? Here's our testing. When we did our testing with a DGX A100, when you look at this testing as a note here, this is tested with 2 of our Pavilion boxes, tested with 1 and extrapolated to 2, right? By carving up the DGX in half and then adding another half for all intents and purposes. We could test with file on the left. I'm not gonna go through the details and explain it. You can look at it later. File details on the left, block details on the right. I'm gonna look at the file, the green one on the left. The 2 bars on the left are read performance. The 2 bars on the right are write performance. The blue bars are using GPU direct storage. The orange bars are non-GPU direct storage. In other words, on the orange, the data goes from the Pavilion box through the NICs to the CPU, and then the CPU loads all 8 of the GPUs. The blue box goes from the Pavilion box through the NICs and directly loads the GPUs. So we were able to deliver, why the numbers are 2, the black ones are GIB, that's the way NVIDIA typically calls them. I'm also giving in the gray the gigabytes per second. So we delivered 191 gigabytes a second at 1.75 millisecond latency. That's the white numbers. That yellow number of 1628 is the number of CPU, what percentage of the CPU was utilized to deliver that work. This is a testament to the GPU direct storage. By doing the blue, GPU direct, we were able to deliver 2.5 times the performance, leveraging 16% of the CPU versus 28. You may say, well, that's not really important in the CPU world. Those 2 CPUs that are in that DGX are a sum total of 256 cores. So that frees up a lot of CPU to do a lot of different things. Similar performance, whether it's block or file, right? You can look at our write performance, incredibly impressive. Again, when you go talk about our competition, some of these numbers are out there published out on the web through different articles. Go do your homework, go out and look for those things, and then ask the questions. What was their write performance? What was their latency? Because you'll see most people don't publish their write latency. They don't publish their write performance. Typically, when you don't publish something, it means it might not be that good. We publish all our numbers and we'll go up against anybody. We're getting a lot of recognition out in the press as well. This is a quote from Chris Meller, one of the journalists was the major editor and journalist for Blocks and Files out of the UK. His quote was, "I think Pavilion has given DDN, VAST, Data, Weka IO a hard problem as your system's superior hardware architecture accelerates file IO beyond their limits." Very impressive. There's a quote. You could go to Blocks and File to go see some articles he's published in this space. He's pretty innovative and out there challenging all of us out in the marketplace. So we're really proud of that. And thank you, Chris, for the great quote. Again, you may not need, even in a big DGX world, or a big GPU world, need 190 gigabytes a second file. to one DGX. One of our large customer uses a bunch of HPE servers with NVIDIA GPUs in there, and it takes about 12 of those to saturate one of our boxes running Spectrum Scale, as an example. Another customer may take 4 or 5 or 6 to saturate one of our boxes. So don't think it has to be, I don't need 191 gigabytes a second, so I don't need one of these things. We give you that flexibility and choice, whether it's one box or multiple boxes, because those are just a hero number of what throughput, how much water you can run through the pipes. Then you got to run your applications on top of those things. We give you both. So don't just think super, super high performance for one box, one DGX or one big GPU enabled server. We can make multiples of those things scream. So I talked about flexibility and performance. I talked about the flexibility of our new Pavilion HyperOS. I talked about our NVIDIA partnership. Let's wrap up with some solutions and use cases, and we'll close with any questions. If you have any questions, feel free to put them in the chat or the Q&A, and we'll address those. If not, feel free to, we'll open it up. So here's an example of one of our large government customers that is a very, very large Spectrum Scale environment. It's an environment where they started with 3 of our boxes and several of their servers, and then they deploy 3 at a time, expanding out to a very, very large IBM Spectrum Scale environment on the road to 11 of our boxes, right? Today there's 3, there's 8 more in test that are going to be put in production shortly. When they do their testing, they test in this cluster of 3. Their performance testing has given us up into the, my apologies on, we put the wrong slide in here. It's 100 gigabytes a second read and 75 gigabytes a second write for a single box. We replaced the competition that was the incumbent out there and delivered over 40% read performance, 60% better write performance and their size was 150% our rack unit, so much bigger in physical size. So our future is they're on the road to multiple Pavilion boxes with over $1,000 to $2,000, $75,000 GPU enabled servers, right? One of the quotes from the partner when they originally did their testing, right? This was months ago and the numbers are lower. We've improved them as we've gone through. When they first did their testing, he had 28 nodes running, was getting 220 gigabytes a second write. He thought there was something wrong with his test. And the quote from that partner is, Pavilion makes the impossible possible. That same scalable performance can be used for very large VMware environments, maybe running analytics applications like Greenplum, which is one of our customers out in the UK. There's other customers that are running virtualized environments with containers and maybe running Splunk on this. At the end of the day, we're giving these virtualized environments that have hundreds and hundreds of servers that expect consistent performance for every single server. And when you're in a virtualized environment, you want to deliver the most IOPS, the most latency, the most throughput. Sometimes it's big blocks, sometimes it's small block. So you want a platform that gives you that flexibility. When we originally won that very large VMware environment, it was about a couple of years ago. When we first run the RFP, we were narrowed down to 2, and the RFP said you had to have X IOPS, X latency, blah, 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 very high performance. One of the competition took them 16 of their boxes to deliver that performance. We won the RFP with 1.5 of our boxes, testament to our architecture and our performance. In that environment, we have vCenter plugins and we have Kubernetes drivers, all the things to help manage that ecosystem. Keith alluded to media and entertainment. Sony Innovation Studios is one of our marquee customers who's using this thing for something called volumetric capture, which is these special cameras with multiple cameras doing all this ingest and doing data analysis to eventually do 3D imaging and 3D games and 3D movies, all leveraging Spectrum Scale, Pavilion, as well as the Microsoft environment, right? So you'll see in media and entertainment, moving into Windows NVMe over Fabric is very important, especially in this post-production world. SQL Server, as I mentioned, we have large financial funds doing very heavy analysis, whether they're a hedge fund or service providers, and they're deploying very large SQL servers. in chunks of 4 and delivering huge throughput and huge IOPS in a very simple, consistent, scalable manner. And then as we summarize into these use cases for fast NFS and block, there are many use cases leveraging many different kinds of software and hardware technologies. And we're providing solutions for everything from AI to log analytics to virtual infrastructure to high frequency trader, high speed sensor ingest. At the end of the day, what those applications are doing, solving those problems, at the end of the day is the end user applications, we help them run faster, perform more consistently, and scale larger. And as we look into the future, there's several kind of unique deals that we're working on is things for our big high performance parallel file systems and medical research where you have, very sophisticated electron microscopes ingesting data at the same time while people are running analytics on that and doing tools all in a very high performance, high capacity, high throughput analytics environment. People that are doing multi-sensor ingest, maybe there's applications out there from satellites delivering satellite imaging or cameras all around cities, ingesting data where you're having these in-memory databases like OmniSci or another one of these analytics tool called Clarif AI that runs on NVIDIA platforms finding out all the people that have a handgun or people that have an AK-47, all these kind of analytics on these things, leveraging GPU technologies, but requires very high speed ingest, but also high speed performance and analytics. So it gives us that ultimate flexibility, even in the financial analysis, doing things like all sorts of tick data getting ingested and all sorts of data from all sorts of data points, ingesting data into a high performance parallel file system and doing very, very high performance analytics on that to give trading information, for example, or trending information. So it gives you that flexibility. For us is multi-input, multi-format, multi-user, big data input, small files, processing solutions that drive high performance scale out file systems. So if we summarize that, we're faster than the speed of light, whether it's block, file, or object, all in that 4 rack units. Here's our hero numbers for block, file, NFS, object, leveraging out into spectrum scale or our luster testing. You'll see later, I have to check backwards, we're almost finished with our BGFS testing. A little bit of answer. Our BGFS numbers look closer to that spectrum scale number than they look closer to the luster number. And again, as we summarize all these use cases, right, is delivering more data faster, allowing customers to get more insights and analytics and data into their ecosystems. So when you think of Pavilion, we're enabling unrivaled data storage, choice, and control. With that, Keith, I'll turn it back over to you for any questions.
Thank you so much, Costa. That was fabulous. So if anyone has any questions, please feel free to go ahead and either put them into the questions or into the chat, and we'll go ahead and address them. And we did have a question that came in during the presentation. And you kind of answered it, Costa. The question was, are our performance numbers using RAID, using RAID, or are they just straight stripe drives? And you did mention that we do all of our testing using RAID 6. But maybe you could talk a little bit about some of our other RAID enhancements and how we provide high-speed data recovery in the event of a drive failure, how we rebuild drives faster than.
That's a good question. We use RAID 6, which is incredibly efficient, right, and incredibly fast for what we do, dual drive parity protection. We actually have a patent on a technology that we call Swarm. So we have the technology because we can engage multiple controllers. If a drive fails to do a RAID rebuild, we can rebuild 1 terabyte every 5 minutes. So if a 15 terabyte drive dies, we can rebuild that drive in 75 minutes. That takes our competitors days to rebuild, let alone now it's coming to a 30 terabyte drive, right? So at the end of the day, not just RAID, really a great way to get you back out of the degraded state and back into a normal protected state.
That's fantastic. All right, and just one other question. So one of the comments that was made earlier was that when someone's using, say, a GPU-based system to go ahead and perform analysis on data using the internal drives, moving to an external solution like Pavilion, what kind of performance deltas can they expect by moving from internal to external drives?
Yeah, and what I was showing with one of our customers that we tested, they got almost the exact same performance testing with the drives inside their DGX. Happened to be a DGX, wouldn't matter if it was just an HP server with GPUs, doesn't matter. Similar performance to actually running NVMe over Fabric, in the case we tested was Rocky or RDMA, to a Pavilion box. They got almost the exact same performance. There are other use cases we've gotten better performance because of the parallelism of what we can do. So it all depends on your application, but you expect similar to better performance. And the big benefit of that, the use case for that customer, there was one of them, that's a classified thing, but one of their analysis was to analyze a set of data. And because of the capacity they had inside the DGX, it was only 4 drives, they could only analyze 1 year's worth of data. They wanted to analyze 30 years worth of data. So we gave them the flexibility to put that data outside the box and give them similar performance. Back to you, Keith.
Thank you so much, Costa. That's been excellent. And at this point, I'd like to thank everyone for participating in this webinar. A recorded version of it will be made available to you as soon as possible. Thank you again, and we look forward to speaking to you again soon.